For lesson 66, we're working with polynomial equations. A lot of the equations that we've been working with up to this point have been linear or quadratic, but now we are slowly diving into higher degree polynomials. For instance, 2x to the fourth minus 10x to the third minus 72x squared equals 0. You have been taught from day one, if there is a GCF, to go ahead and factor it out, correct? So let's go ahead and do that. 2, 10, and 72. Factor out the 2. And what else can I factor out along with it?
X squared.
X squared. Leaving us with x squared minus 5x minus 36. Can we do anything else with this? Got a quadratic on the inside, so we could possibly reverse FOIL. Factors of 36 that you would like to use.
9 and 4.
9 and 4 would be two good ones. Negative 36, one has to be negative, the other has to be positive. We want a sum to be a negative 5, therefore negative 9. So this is really nothing special. You've actually worked with these before. Now we set these guys equal to 1 or equal to 0, and then solve. So negative 4, positive 9, and what would x be here? Yeah, 0. You could divide by 2 and then take the square root, but we know it's going to be 0. There is this idea, it's called the fundamental theorem of arithmetic, that states that, in theory, whatever our degree is, that should be the number of solutions that we come up with, or possibly could come up to. So if we go back to this one, what was our degree? It was 4. And how many solutions should we have come up with? 4. Okay, but obviously we only came up with 3. So we have to have some reasoning or explanation behind it, and the reason is multiplicity of roots. The multiplicity of roots just simply states the number of times that root can occur. For instance, well, let's go ahead and look at example number 2. They want us to find the roots, as always, and then they also want us to give the multiplicity of each root. GCF, okay, I see a bunch of x's, so we can factor out 3 of them. Leaving us with x squared, 8x, 16. Factors of 16 that you want to use? 4, obviously. Yep. And then I have x plus 4 again, which I'm not going to write because I know that's also going to be negative 4. So for my roots, I have negative 4. I also have 0. But again, we came up with fewer roots than there is the degree. So again, the reasoning behind that is the multiplicity. So this is the first part now. The last part is give the multiplicity of each root. And the multiplicity simply states, well, how many times did that root appear or occur? And if we go back to 0, x to the third is equal to 0. How many times does this one occur? 3 times would be your answer. So here's what you need to say. Root 0 has multiplicity of 3. Why? Because it occurred 3 times. I know that because of the exponent of 3 right there. We could say x times x times x. And our other root would be 4. What would its multiplicity be? Not 1, but 2. The reason is because it showed up here and it showed up there. It showed up twice. It's the number of times that it occurs. And notice if we add up our multiplicities, what do they add up to? 5. 3 and 2 will add up to that degree of 5 that we began with. So there's the reasoning behind it. Okay? Even though we did not match our degree, the multiplicities, the number of times that they appeared, did. Let's go back to example number 1, and let's identify our multiplicities here. Again, degree was 4. We had 3 roots. How many times did this occur? The negative 4. Just once. Multiplicity of 1. How many times did this occur? Once. And how many times did this occur? Twice, because this exponent of 2. What do they add up to? 4. And maybe our favorite problem of the semester, we get into this thing called the rational root theorem. Don't worry about writing this in your notes, but I'll go ahead and read it off. If a polynomial p of x has integer coefficients, then every rational root of p of x equals 0 can be written in the form p over q, where p is a factor of the constant and q is a factor of the leading coefficient. A little wordy, am I right? Okay, so let's walk through this first example and I think you'll pick up on the process. If we look at this one, do we have a GCF? No, we do not. It's cubic, and we really have no methods to solving a cubic except for factor by grouping. But I think if we tried that, it wouldn't work out for us. So we have to move on to something different. Okay? And our ultimate theorem that we can go to is this rational root theorem. So here's what we need to do. Start by identifying your leading coefficient as well as your constant term. Okay? Per the definition, they're calling the constant term the p, and the leading coefficient is now the q. And what we want to do is identify all the factors of p and q and write it in the form of p over q. Once again, p is 12, so let's start listing the factors of 12. Well, we have the trivial case of 1 and 12. It's even, so we know 2 is a factor. And then I also know 3 and 4. Factors of q. What's our leading coefficient here? 1. And I will tell you, the smaller the number, the fewer the factors, the easier this problem will be. So the only factor of 1 is going to be 1. And what the rational root theorem does for us is it indicates to us, hey, this is the list of all possible roots that it could be. The first combination, and the other thing I need to add here is plus or minus. So we could have a positive 1 over a negative 1, or we could have a negative 1 over a negative 1. We could have a positive 1 over a positive 1. So if we create this list, one of the roots could be positive 1 or negative 1. Another root could be positive 2 or negative 2. Could be positive 3 or negative 3. Could be positive 4 or negative 4. Plus or minus 6, plus or minus 12. So somewhere within this list lies all of our real roots that we are searching for. The problem is we don't know which ones they exactly are. The good news is you've been taught a process to identify which one the real root is. And that goes back to our remainder theorem. Synthetic division. If we use synthetic division, what remainder are we looking for? 0. So here's what you need to do. You need to start by picking one of these. Okay, I would start with 1 or negative 1. And what you need to do is it's really a guess and check at this point. Fill in your coefficients 1, -2, -11, and 12. And we need to use synthetic division to see if indeed 1 happens to be a root. If it works out that it's not, we can eliminate 1 as our possibility. Drop the 1, multiply, add -1, -1, -12, -12, and wouldn't you know it, we did come up with that remainder being 0. So that's good news for us. Because at this point we know that this positive 1, it's a root. So let's go ahead and write this down. Root, colon, 1. Now the even better news for us is now that we have found this, what we've done is we've actually created a quadratic down here. Recall if we did synthetic division, this was your remainder, this was your constant term, this was your x, and this was your x squared. So let me go ahead and show it this way. X to the third minus 2x squared minus 11x plus 12. That was our original polynomial. Well, now that we found that 1 to be a root, what we can say is x minus 1 is a factor of it. And now this here, this is what's left over. X squared minus 1x minus 12. So really what has happened is we've taken our cubic and factored it down to a binomial and a trinomial. Everybody okay with that idea? And now if this was a really nice problem, we already know 1 exists. Maybe this thing could factor for us, so we don't have to do the guess and check method anymore with synthetic division. But instead, see if it factors x, factors of 12. Well, 4 and 3. We want that 4 to be negative, 3 to be positive, to get a product of -12, but a sum of -1. And lo and behold, 1, -3, and 4. So there are our roots. What was our degree to begin with? What was our degree? It was 3. How many solutions did we come up with? 3. Therefore, the multiplicity of each one would be what? 1. Okay, have to be. Otherwise, you can't come up with a multiplicity that's greater than your degree. It always needs to add to them. Jacob.
Wouldn't, like, it be x plus 1? X, oh.
Still want to use the idea of x setting this equal to 0. So if this would have been, if we would have tried -2 out here, what would we have wrote down here? X plus 2. That's Kylie.
Wait, so where did you get the numbers in the red? Where did you get that from?
Where did I get what numbers?
Numbers in the red. Where did you get that from?
We got that by taking our factors of P over the factors of Q. And the combinations that you could come up with are any of these numbers over any of these numbers down here. So what's 1 over 1 equivalent to? 1. But also with your plus or minuses, positive over a positive is still positive. Positive over a negative is negative. Negative over a positive is negative. And a negative over a negative is negative. Does that make sense? Would you agree that 3 over 1 is 3? Yeah. 6 over 1 is 6. 12 over 1 is 12. Then just add the plus or minus there. Sean?
So if Q, let's say Q is 2, so would you divide 1 by 2 also?
Yes. Let's do another one. We're not going to do the entire problem, but just so we can come up with that list of P over Q. Let me give you this one. Let's go 2x to the 4th minus 3x plus, I don't know. Let's go 6. It's to the 4th. We can't factor out a GCF. Therefore, we don't know how to solve a quartic equation. So again, rational root theorem, it's our default because we can use the rational root theorem for any given equation. But again, let me get this straight. The 2 is our q. The 6 is our p. And we want to come up with the list of p over q. So let's list the factors of our q, which would be what? Or sorry, let's list the factors of p since that's our numerator.
1, 2, 3, 6.
Yes. And the factors of q? 1 and 2. So when I go to create this list of possible roots, let's start by putting everything over 1. So I have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. That's good. Now let's put everything over 2. 1 over 2 would be a half. So positive 1/2 or negative 1/2 could be a root. Not saying that it is, but it's a possibility. 2 over 2 would be 1, correct? So we don't need to list it again. 3 over 2, we haven't listed that one yet. And then 6 over 2 would be what? 3, which we already have that as well. So just be aware of that. If you already have it, don't add it to the list. So now we have 1, 2, 3, 4, 5, 6 numbers on the board. Plus or minus indicate we have 12 possible roots. And again, my advice to you, start with 1 or negative 1. Because chances are, more times than not, that's one of your roots. Questions?
Okay, so whenever you do this synthetic division or whatever, after you get those roots, like that box, that one right there.
Uh-huh.
Where did you get that one from?
This one?
No, the one on the top left.
That one?
Where,
I just picked it. I went to my list of possible roots, which is this list right here, and I just picked the very first one. I'm going to try 1.
but it works for all of them?
No. It works for these 3 right there.
Okay.
If you guys would have chose to do negative 3, would it have worked out?
Yes.
Yeah. If you would have chose 4, would it have worked out? Yes. Okay, and that's kind of the crazy thing is it'll work for all of your roots. Okay. If you would have tried negative 1, it wouldn't have for any of those. So when you start this process, just pick the very first one in your list, see if it works out. If it doesn't, cross it off your list, move on to the next one. And then once you find that first root, again, the process will become a little bit easier because now you can go back, you can use these values here to create your trinomial that you can factor. Hopefully it'll factor for you. Sound good? Why don't we take a few minutes? A couple of problems that I want you to work on. Let's do C as well as E. C and E. C and E.